Let's do another example. Let's find the min max of f of x comma y equals 3xy minus x cubed minus y cubed on x greater than or equal to negative 1, x less than or equal to 3, y greater than or equal to negative 1, y less than or equal to 3. So this time, instead of drawing a picture, the question just provides some inequalities. That shape happens to be a rectangle, doesn't it? Right? Or a square, right? X bigger than negative 1 but smaller than 3, y bigger than negative 1 but smaller than 3. That's a square that looks like this. When we first compute critical points, we'll take partial derivative, set equal to 0. By the way, when you set f sub x equal to 0, you end up getting y equals x squared. When you set f sub y equal to 0, you end up getting x equals y squared. So now you have y equals x squared and x equals y squared. Now what? Well, we just substitute, right? So how about we substitute a y squared whenever we see an x in y equals x squared, and you get y equals, oh, there's an x to replace with y squared, then there's still a square. So you get y equals y to the fourth, right? So y to the fourth minus y equals 0, you can factor out a y, and then it's a little more work to factor the difference of perfect cubes, but ultimately you get y times y minus 1 times y squared plus y plus 1 equals 0. That third, so you split this up into three separate equations, and it turns out y squared plus y plus 1 equals 0 doesn't have any real solutions. You just run this through the quadratic formula. So the point is we get two values of y that work, y equals 0, y equals 1. By the way, y equals 0 together with x equals y squared, well then x equals 0 squared, so x has to equal 0. So this is saying that 0, 0 is a critical point. The other value of y that worked was 1, and if you look at y equals 1 together with the fact that x is equal to y squared, so x equals 1 squared, that leads to x equals 1, so 1, 1 is a critical point. So the only critical points that we found are 0, 0, and 1, 1. There are none other. Both of those points happen to belong inside the interior of this square that we have labeled with a capital R. Okay, so those are our partial derivatives again. We have these two critical points, 0, 0, and 1, 1. Now let's apply the second derivative test. So we'll compute some second derivatives. Look at the discriminant, right? So negative 6x, determinant of negative 6x, and then 3 is copied in two places, negative 6y. So this ends up being negative 6x times negative 6y, which is a positive 36xy, then minus 3 times 3, which is 9. This, by the way, if we compute the value of the discriminant at the origin, you get negative 9. So with the discriminant being negative, you have 0, 0 as a saddle point. If we plug in 1, 1, you get positive, so you get, 36 minus 9 or 27. The point is you get a positive number, so we have a local extremum, meaning we need to now compute f sub xx at the point 1, 1. So staring back up here, we're going to get for that the number negative 6 times 1, or negative 6. That's a negative number, which means that you have a local, let's see, that means you have a local max, right? Okay, you have a local max at 1, 1. Okay, so cool, we have a saddle point, and we have a local max, and we might as well compute z values. So go back to the original function, plug in, at 0, 0, the z value is 0, and at 1, 1, the z value is 1. The whole purpose of computing that is because when we're trying to find global mins and max, we now need to check what happens on the boundary. So what happens on the four edges of the square, and we want to compare those z values to these z values of 0 and 1. Okay, so now we'll check the boundary. Okay, so the bottom edge of the square happens to be, so I've written the boundary, written the square in a much more compact notation here, so it's kind of a lot easier to read what's going on. The bottom edge of the square, for instance, y is equal to 1, while x ranges between negative 1 and positive 3. So what we're trying to do then is, okay, fine, y is always negative 1, so let's plug in negative 1. In the end, once simplifying, we're looking at the function negative 3x minus x cubed plus 1, which we've named g of x. We're trying to look at that for x values between negative 1 and positive 3. So fine, to do that calc 1 style optimization problem, take derivative, set equal to 0. Unfortunately, there are no real solutions. So fine, we don't have to check anywhere on the interior of that line segment. We do need to check the boundary though. So we'll just compute for this function g what happens at the smallest x value and the largest x value that we care about, and we get z values of 5 and negative 35. let's check the top edge of the square. Okay, so we check the bottom edge, but actually before doing that, let's just draw a picture of what we have so far. So we had a saddle with z value 0, we had a local max on the interior with z value 1, and then all along this bottom line segment, there were no critical points in the interior of the line segment, but we still had to check endpoints, and we got z values of 5 and negative 35. So now let's check the top edge of the square, right? And on that top edge, y is equal to 3. We're going to be looking for x between negative 1 and positive 3, though. All right, so what do we do here? Let's name a new function. All along, y is equal to 3, so we'll just plug that in. In the end, in a simplified form, we're looking at the function 9x minus x cubed minus 27. And we're going to maximize or minimize that for x between negative 1 and 3. So take derivative, set equal to 0. You do end up getting two solutions, x equals plus or minus root 3. Of these solutions, though, here's the thing, x equals negative root 3. It's not in the interval we need. So just throw out x equals negative root 3. We only need x equals positive root 3. Here, we would have done this in Calc 1 as well, if we're looking only at x values between negative 1 and 3. So then, let's compute what the z value is at this x value. So, plug in, we're still plugging in 3 for y, but now plug in root 3 for x. And sorry for the calculator work, but this ends up being approximately negative 16.6. So I'll say, how do I say this? So the types of questions I plan to be asking you all for quizzes and such don't require a calculator, but sometimes a better question to illustrate the concepts might be sticky enough that using a calculator is helpful. So we got a z value of negative 16.6 for that critical point, but we do need to check the endpoint. So we need to check what happens at the boundary when x equals negative 1 and when x equals 3, and you'll notice we get z values of negative 35 and negative 27. Now I note that we could have gotten this negative 35, so when x equals negative 1, by symmetry, because take a look at the function 3xy minus x cubed minus y cubed. That would all be the same if you swapped the roles of every x and y. So what I'm trying to say is the fact that we got this negative 35 over here before, we could, because of this kind of symmetry, we could have copied that over. That would have flipped over along the line y equals x to produce this negative 35 right here. So otherwise, that critical point we got in the interior where the z coordinate is negative 16.6, I've labeled that here. And then the two endpoints where the z coordinates are negative 35 and negative 27. Because, again, we have this symmetric in x and y business, what we can do is we should technically check the left and right edges of the square, but we can now actually just copy info because all along this diagonal line here, y equals x, that should be a mirror for this problem. It just, we got lucky because of the shape of the problem, so we'll copy that negative 16.6 here. And those are all of the points we need to have labeled. All right, so then looking at this overall, yeah, this picture is symmetric along the line y equals x. So we didn't have to compute, yeah, that was the point. We didn't have to compute both negative 35 separately. So looking at all of the z values that are shown here in red, we had local max, was it? What's local max, local min? Anyway, we had an extreme value where the z value was 1, and we had a saddle at the origin. We had global min, let's see, staring at all of the z values shown in red, the smallest is negative 35, so that happens at 2 boundary points. And then the global max, the largest z value happens right here, z is equal to 5, at the boundary point, typo here, negative 1 comma negative 1. So let's take a look at a picture of this. Okay, so you're seeing currently all of the points where the output or the z coordinate is 0.5, and if we start decreasing this, you can see I'm looking actually at the corner. Oh, look right there. So you know this spot right here, the output is negative 17. We saw like a negative 16.6 or something like that if I recall. So fine, that's just if you look on the line segment, but the point is if we keep pushing this a bit more, right there at this corner, now we're getting z value negative 27, but that's not where the smallest z value is anyway, because look, it looks like we should keep going with this. Yeah, there we go. And then right there at this corner, right? So let me undo that. Stare at the upper left corner, and right about there somewhere. that looks to be now our global min. For the global max, we're going to extend the value, increase the value of k. We see right here the evidence of a saddle point, and if we keep increasing k, you'll see here we go, right about there. There we go. And now that is the largest value of z for a point in the square. Of course, we can keep increasing k, and here's larger values of z out over here, but those are not in the square, and we were told that we had to optimize within the square.